Okay, let's go to part 2, chapter 23, and it's going to be calculating the electric potential when we have a continuous distribution of a charge. For example, we have a charge on this solid, the total charge is Q, and we're looking for the electric potential at some point right here, for example. So what do? Well, we take a segment, write a quantity, write the Q of that charge, correct, and we go to that point, correct, using these quantities. And to do that, we have some formulas that we found in part 1. In part 1, we found that when we have a distributions, we can use this equation using integers, or we can use this one using the electric field. If we are using this, right, the electric field is found using the Gauss or Gauss's law. So this is found first, and then we apply right here to find the potential difference, right? The electric potential. Okay, perfect. Let's do it. Let's just start with this equation using the electric field, and let's calculate the electric potential for a sphere. Correct. For the sphere, imagine that we have a sphere, and this sphere is charged, and the radius is r. Okay, and the charge is positive. Okay, positive charge. Perfect. Let's try to find the electric potential inside and the electric potential outside. Okay, inside of this charged sphere is found that the electric field, right, is equals to 0 using the Gaussian surface. Right, there is no charge inside, so the electric field is 0. If the electric field is 0, what should be the, we can use this one if you want to. If the electric field is 0, what should be the potential difference? Well, it's gonna be 0. Means what? If we could define this as the electric potential at A minus electric potential at B is equals to 0, for example, or B minus A is the same idea, B minus A. So what do we have? We have that V at A is equals to V at B. Conclusion that the electric potential inside of this conductor is gonna be constant, is the same. Now, what about outside? Outside. The same thing, right? Let's find the electric field outside. The best way, remember, is using the Gauss's law, right? And it's found that actually this electric field is equals to K by the total charge divided by R. If we're using as a vector, because we need to use this integral, it's gonna be the same thing, right? In that way. So now let's go back to this equation. So this product is equals to the electric field, right, is radial because it's a sphere, right? It's a sphere, and the same thing happens to the to this delta L, right? It's gonna be in the same direction, right, as the electric field. Okay, perfect. Now, what do we have? This equals to the electric field or in the radial direction times, right, the R. When we, because again it's parallel, the cosine, we're dealing with cosine, remember when we have that product is cosine, but let's do vector parallel, the angle is 0, cosine 0 is 1. Okay, great. Let's go to find the electric potential. So it's equals to negative integral of the electric field is found is this. Well, this equals to what? For the charge, this Q we just found this right here, right? It's gonna be KQ over R dr. Right, from where to where? From infinity, right, to the distance R. Also remember, this is just the electric potential at R, right, minus electric potential, right, at infinity. But at infinity, right, is approach to 0 because this R is large R, right, and this becomes 0. Perfect. So this is equals to what then? This is equals to KQ negative times negative, right, 1 over R from 0 to R. Correct? And what should be then this electric potential is equals to just to K the total charge divided by R, right? Which is the same as for a point charge. They have the same form, right? When this R is greater than R. What should be when R is equals to R? Well, just plug the value big R right here, right on the surface. Okay, perfect. Now let's try to find a graph that relates the electric field and the electric potential for this sphere. Okay, let's do it for this sphere. Okay, let's do it. We have that the electric field for this sphere behaves in this way. Right? At the center, we found that inside is 0, right? Inside is gonna be 0, correct? So at this point, where it is at the edge, of course, the electric field is KQ over R, big R squared. But what happens outside? Outside behaves as a point charge, right? As a point charge, right? And it goes like that. This is the electric field equals to KQ over R squared. Remember, this is R, okay? This is R. What about for the electric potential? Well, the electric potential we found this is the electric field is 0, right? The electric potential is gonna be this is not 0 right here. 0 is here, right? 0 is here. Okay, inside is 0, not right there. Okay, this is actually the quantity in that way. Okay, perfect. Now, right here is gonna be constant inside, right? Constant. And what is the value inside? Okay, V is equals to KQ divided by big R. And inside, of course, decreases in this way. V, right, electric potential is KQ over R. Correct? And this is the behavior of the electric field and electric potential when we have this charged sphere. Okay, now imagine that we're looking for the work done to charge this sphere. Let's find how much work is required. And the work that is required is the same as the electric potential energy of this sphere, right? It's similarly to when we are dealing with gravitational potential energy, right? We have to do work to change the potential of this object, right? From here to here, we have to do work. We do work, we change the potential, right? If this is done at constant velocity, right? The work is equals to the change in potential. The same thing happens over here. Let's find the electric potential energy for this charged sphere. To do that, we need to find the work done to charge the sphere. Okay, let's do it. Let's just start with this definition, right? It says that well, we can say that V, right, the electric potential is equals to work, right, divided by the charge. Okay, perfect. What should be work then? Is equals to electric potential times the charge, correct? Or we can also do this, right, taking infinitesimal work to moving these small charges. And then what do we have? Well, work is equals to the integral of this electric potential dq. Perfect. Now we're doing work to charge this sphere. In this way, we take a charge from infinity and place it on the surface of the sphere. Another charge, right, then place it on the surface of the sphere. Right? So when we're dealing with charges, because again we're dealing one charge by one, so the electric potential is equals to this representation, right? So it's equals to the integral of KQ over R, right, dq. and the charge goes from 0 to the total charge, right? The total charge is Q, BQ. Okay, so what should be then the work? In this case, the work is equals to K over R, right? Q squared divided by 2. Perfect. One more time. So the work is equals to, the charge this sphere is equals to K Q squared divided by 2. But which R is this one? At the distance, it's gonna be right from infinity to this R, right from infinity to this R. The radius of the sphere, correct? The radius of the sphere. And that's gonna be also the electric potential energy of the sphere. Perfect. Now let's go to the next topic. The next topic is equipotential surfaces. Let's do it. Equipotential surfaces. Equipotential surfaces. Okay. Equi means equal potential, the same potential. So we have a surface that has the same potential, right? These 2 points, right, have the same potential. Okay, now let's work with this in relation to the electric field. Let's see how they are related. Perfect. This is voltage, right? The electric potential. Great. Now we can use one of these equations. We can use, for example, this one, right? We can say that this change in the electric potential is equals to negative, right? This dot product, correct? But look what happened. This means change. We can use also this one. You want to look this one that give us the change. This one, right? To make it easier. The idea is the same. Okay, so we have as any more change that happened. Here's more change, right? Because this surface has the same electric potential, so the change is gonna be 0, correct? We take this point, what is the change, right? It's gonna be 0. So it's equals to what? Negative this product, a cosine theta dl. But of course the electric field is not 0, and this element is not 0 either, right? So the only condition to get 0 is this factor. So cosine 0 must be equal to 0. Okay, and when that happens when the angle is 90 degrees. Means that to get a 0 change in potential, electric potential, right? The condition must be that this electric field must be perpendicular to this element. But this element of distance length is or belongs to, right, the surface that is at the same potential, right? So we can use this element, or we can use V to get the same condition, right? So it means also that the electric field must be perpendicular to the equipotential surface, right? Or to V, the electric potential, right? So these two must be perpendicular to get these conditions right here. Perfect. For example, imagine that we have this point charge, where we have the point charge, and we know that this is the electric field by convention, correct? This is by convention. It goes away from the charge. This is the electric field. Now let's find the equipotential surfaces. Remember, these two must be perpendicular. The electric field is perpendicular to this equipotential surface, right? Well, we can use that way, or we can use right this way. The idea is the same. Imagine that these are the surfaces one more time, right? That have the same potential, electric potential. Perfect. For example, if this is 100 volts, this one gonna be less. Let's say 30 volt, for instance. Right? Decreases the electric potential decreases, you are moving away from, in this case, from the positive charge, right? Because of this condition, this equation. Great. Now let's see, let's make a graph that represents this behavior. The behavior. Okay. Imagine that this is the electric potential, right? Now it behaves according to this equation. Look at this equation right here. It behaves in that way, correct? Like that. Where of course this line, right, is gonna be at this position, right, in this line, right, and so on. Correct? This is for a positive charge. What about for negative charge? For negative charge, a negative charge is gonna be again the behavior. One more time. Not gonna be like this. In that way. For a negative charge. Of course, we have the same picture right here, and for the equipotential surfaces or equipotential lines. Great. Now, what happens if we have positive and negative? Again, this is positive, okay, positive. Now, what happens if we have positive and negative? Let's combine them. Okay, let's do it. Let's do it. If we have positive and positive, right, or positive and negative at the beginning, okay. Remember, this is the lines of reference, okay. And for positive, right, behaves like this, correct. For negative, it behaves like this, imagine. When we combine this, of course, this is the behavior at the beginning. When we combine them, it goes in this way. It goes like that, and it goes like this. Can you see it? This is for positive and negative charges. This is the electric potential. Now, what happens if we have two positive charges? Okay, how it looks like? The same thing, right? It's gonna be the reference line. For one, remember, goes in this way, correct, like that. For the second one, it goes also like this, right? Like that. But when we combine them, of course, this one behaves in this way. Because they repel a little bit. This one stays about the same, right? And this is gonna be the electric potential for these two positive charges close together. Okay, perfect. Now let's go to the last topic of this chapter. The last topic is gonna be the potential gradient. Okay, the potential gradient is this vector, right, or gradient, okay, potential gradient. That's the potential gradient. In this case, we use partial derivatives. Perfect. Let's do it. Let's just start with this equation right here. Right. Let's just start with this one again, or with this one. So they're the same. Okay, it's gonna be this no change in the electric potential is equals to negative, right? This dot product, correct? Now, what is this? This is equals to negative E cosine theta dl. Perfect. Now, this is a component of the electric field. Let's make this the component of the electric field. S of L equals to E cosine theta. Correct? Imagine that this is the case. Imagine we have this electric field like this. You might have a point charge right there, right? And we create that equipotential surfaces. What should be the electric field? Well, The electric field goes from here to here, right? This is high potential. High potential is gonna be low potential. Remember, when we're dealing with positive charges, which is the charge that moves, right? We take always the electric field going from the high potential to the low potential, correct? And imagine that we have this line, correct? This line like that. Imagine. So imagine this is the electric field at this point. What should be then? That is the electric field. What should be? Let's make it shorter, right? That direction. Imagine this is the electric field in this direction. What should be then this of L? Well, this is the electric field. Now this is the direction. This is the component in that direction, right? It's gonna be. This is gonna be this is of L, correct? And this is the angle theta. This is the way how they are related. Okay, perfect. And then what do we have? Well, from here we have that this element of this electric potential gonna be equals to negative this component times this element of length. Correct? And then from here we can find this component right here, what equals to this difference, right? This change, right? It's gonna be negative in this way. But look, imagine that in general, we're looking for the magnitude of this electric field. Actually, we're looking for the direction. How we can find the direction of the electric field? The direction of the electric field is the direction on which this rate, right, is the maximum. Okay, when this rate is the maximum, is the direction for this electric field. So how we can find the electric field? Imagine that we have this part, right, these components of the electric field. How actually we can find the real direction of the original electric field, because it's a component. Now, what should be again the direction of the electric field? The direction of the electric field is the direction on which this rate, right, is a maximum. It's a maximum. For example, let's do it in this way, an easy case. Let's do an easy case. How we can find the direction of the the electric field. Okay, perfect. When we're dealing with the change in this direction of the electric potential. Okay, let's do it in this way. For simplicity, imagine that these are the equipotential surfaces right here, for example, and this is the electric field. Correct? And we get a component, right? This component in this way, right? In this way, imagine. Okay, for simplicity, let's see if this is, let's say, 4 units, this is 3 units, this is 5 units, right? Let's make a triangle. Okay, now imagine that in this case we're dealing with this equation. Look, to make it easier, this one. Okay, look, the electric field is equals to the change in B, right? The potential difference divided by change in, let's say, in X, or change in R, okay? Change in R in general, change in R. Okay, let's see what happens. For case 1, this is case 1, because look, we're moving, right? Okay, we're looking for the rate. And also, look, imagine this is 20, this is 15, this is 10, and this is 0, for example, right? Imagine. Okay, remember the electric field goes from high potential to low potential. This is both, because we're dealing with electric potential. Okay, perfect. Now, let's see in which direction we have the electric field. In this direction or in this direction. Okay, the definition is that must be in the direction of which this rate um, is the maximum. Let's see, we have these two cases. Okay, case one. For case one, imagine this is case one and this is case two. Okay, for example. Okay, case one. What should be this difference? Well, for electric field, it's gonna be what 10, and for the distance is 5, right? Why is that? It's gonna be 4. Gonna be 2, right? 2. What about for case two? What should be that change in electric potential? Gonna be what? The same thing. Gonna be the same change. Gonna be what? 10. What is the change in the distance, right? It's gonna be now 4. So what is the answer? 2.5, right? And that's the maximum. That's the maximum, correct? So the direction is gonna be then perpendicularly, right, to the, in this case, equipotential surfaces, which is the same condition we found before, right? But it's perpendicular. That's the direction for the electric field. Or when we use a this ratio, right? The same thing, right? We have to find the maximum change, correct? It's gonna be the direction of the electric field. Another way, another example is gonna be this one. Imagine that we have this electric field, right, going that way. Imagine at this point, imagine that we're looking for the electric field direction, the electric field at this point. How we can find it? Well, it must be perpendicular, right, to all of them. We cannot go right like that, because in that case, we can also say, well, we could go in this way. But look, in this way, this distance is more than this distance. So the total rate, right, is gonna be ratio gonna be less than in this case. Now, and at this point, the same thing. This point is gonna be like that. At this point, we're gonna be right like that, and so on. Must be perpendicular because that gives us the maximum rate, right? Perfect. Now let's go back to the potential gradient. Okay, great. Imagine that we're dealing with vectors, right? This is the electric field. Is equals to the same component, right? This is equals to this notation, right? Plus z k hat. Also, because we're dealing with this product, correct? It's gonna be this element is equals to the x, right? I hat plus dy j hat, correct? Plus this z k hat. Now let's go to this product, right? Is equals to negative this vector, right? That this the dot product, right, of E and dl, right? When we do that, uses the dot product, we know that is equals to what? It's equals to ex, right? Is of x, correct? The x plus is of y, right? dy plus is of z, right? dz. Correct. We found again that notation. Now, for example, if we are looking for this quantity for this component of the electric field, it's gonna be equals to what? Only for this one will be this, the total divided by dx. But in that case, we have to make this 0, right? If we make this is 0, in this case, it's gonna be what? This dx, dy, sorry, dy equals to 0 and dz equals to 0. But in that case, we have that the component in this direction is gonna be equals to this ratio, right? But to make it 0, this difference, or when we do that, means that y must be constant, right? And z also must be constant, right? It is a constant, the derivatives are 0. Okay, another notation is this one, correct? It's gonna be the partial with respect to x. In this case, look, in this case, everything's gonna be negative right here, right? It's gonna be negative. Okay, negative, okay, negative. Now, when we use this convention right here, we can get right to this condition right here. Look, we have that this product. Let's continue. Okay, let me do right here. We have now that this is the in this case the electric field is equals to what? It's gonna be equals to negative the partial of v respect to x, right, plus partial of v respect to y, plus partial of z, right? This is the direction, right? K hat in the direction, correct? So we can find then the electric field in that way. Perfect. Now also we can represent this in this way too, right? This is equals to negative negative what? The partial respect to x in this direction plus the partial respect to y, right, in that direction, plus the partial, right, of z in that direction times v. Correct. Okay, this is called the gradient of v, right? Gradient of v, and now this is called a vector operator, right? It's a vector operator, right? Represented by this notation. This notation. This is del or grad. Okay, is a vector operator, negative v. Okay, and this is the potential gradient, correct? This is the potential gradient, right? Okay, again, this is a vector operator represented by this notation, correct? It's a vector, and at the end, what do we have? That the electric field is equal to negative this gradient or potential gradient, right, of B. Got it? Okay, again, why this is important, this equation? Well, it's important in the way that we can find the electric field once we know the electric potential, right? When you know the electric potential, we can derive that and we can get the electric field. For example, right, let's do this case, which is that when we have a charge, point charge, or a point charge. Okay, what should be the electric field? Well, we know already the electric field, right? But now let's use this equation. Gonna be this a negative, right? This potential gradient, right? V. But what is V? What is V for a point charge? Well, we found it, right? It's gonna be equals to KQ over R, right? It's gonna be in this direction, correct? It's because it's a charge, right? It goes right in that direction, correct? So in this case, dv comes right respect to, because in that direction respect to the derivative respect to the distance r. Okay, it's a vector. Okay, so what do we have when we make the derivative? It's equals to what? It's gonna be k, right, q over r squared, right, negative. And then what is this? This is equals to what? This equals to k q right over r squared, which is the charge for the electric field for a point charge. Of course, we need to do more complicated right cases, and then we just, once we know this electric potential, we make the derivative, right, to get the electric field for that distribution. Okay, perfect. And with this, we finish this chapter, and see you in the next chapter. Okay, bye.